It's also my pleasant duty this morning to introduce our keynote speaker for the day, Dr. Christopher Anderson. Dr. Anderson is the Assistant Director of the Iowa State University Climate Science Initiative, which is a research program that provides, and I'm going to have to read this part, authoritative scientific information for short-term and long-term climate-informed decision-making. He holds a doctoral and master's degree in agricultural meteorology from that Ivy League University of the Midwest, Iowa State University. Did I mention I have a master's and a PhD from Iowa State? If I didn't, I should have. Dr. Anderson's research examines linkages between climate variability, climate change, and resource management. He's co-authored recent reports for the Western Utility Climate Alliance and the EPA that contains recommendations on investments in climate modeling that would yield improvements in infrastructure planning for water utilities in major metropolitan areas, flood mitigation in the Midwestern U.S. His current activities are focused on whole farm climate risk analysis, which leads into the talk today. He will be addressing us about extreme weather events, implications for Midwestern Farmscape. Dr. Anderson?
Thank you for that nice introduction. And I like coming down to Missouri. I've been to Columbia here a few times. I have collaborators here. And the reason I like coming down from Iowa to Columbia is I get to see trees. There aren't very many in Iowa. We have a lot around our campus at Iowa State, which makes it very nice. But it's nice to come back and see some trees. Now, give me a minute while I kind of orient myself here to the frame and how I'm going to be able to read my slides a little bit. So here's a pointer, here's advance, and here's behind. Okay, well, extreme weather events is a very broad topic, and instead of speaking about every type of extreme weather event possible, I'm going to focus on warm season rainfall extremes, flood and drought, which seems to be the theme of this research symposium today. And so the angle that I'm going to try to play on this is maybe not so much on the fundamental science of what it is, how an extreme gets formed in the central United States, but more on the side of how extremes have changed recently, what projections are saying about extremes into the future. And so my talk has three parts. One is a reminder of what types of extremes we have seen recently in warm season rainfall. Shibu mentioned some of the events that you've experienced here of floods and droughts. And I will have some slides that focus primarily on Iowa, but you will recognize the same sorts of things that have occurred here. And then I'm going to talk about how people are beginning to use projections of extremes in the near term, meaning 2013, and the medium term, meaning 2020 to 2040, and then in the long term, meaning 2040 to 2100. And then finally, I'll just touch on some of the considerations that are apparent to me for agriculture and agroforestry. And I think these considerations lead well into many of the talks that are going to be held later today. So here's an example from where I live of some of the extremes that we have experienced. This is Ames, Iowa, and we have 4 pictures here around the Ames that shows exactly what we have experienced, and it's quite similar to what I've heard described here. This is our campus at Iowa State University, and this is the year 2010. And you'll see that normally a river, a small creek, in fact, runs along here. And it has overflowed, and it's almost, in fact, penetrated into our football stadium, which means that our football stadium has a better defense than our football team. They're not bad, but let's just be honest. The rest of the university was not quite so well protected. This is our basketball stadium. This is our just a civic center, an area where there's all kinds of different meetings, and over $50 million of damage was incurred in these areas. And what's amazing is that in 1993, when we had similar floods, they built up beyond the 1993 levels by about 3 feet in order to deal with what happens if we have one worse than 1993. And we even beat that. And what happened is the water went over the edges, and what they didn't account for was the weight of the water on things like windows and doors, and it busted in and did a lot of damage. This picture in the upper right is a picture of the drought from this year. This is rolled corn, as we call it. It looks more like straw instead of corn. It's pretty strange looking to be riding around and seeing a big, huge field of straw that's tall, almost as tall as me, in the middle of Iowa. And this is what looks like a beaver dam. It's hard to see because I wasn't able to get down close. It actually isn't a beaver dam, and it's a story I want to save for a little bit later. So to orient you on what kind of extremes these are in terms of the data that we collect for weather is a plot that shows for the state of Iowa from 1873 up to I believe it goes through 2011, the statewide rainfall. And when you look from left to right, you'll see some bars that are blue and some bars are red. The red bars are the years in which there was rainfall that exceeded the 90th percentile. So these are the top 10% wet years. Now, I define this just relative to 1873 to 1980, basically the first 108 years of the record. And so the top 10% equals about 9 or 10 years here in the first 11 years in the first 108 years of the record. But you can see that these 11 years occurred quite over time, over a long period of time. Whereas since 1980, we've had just about the same number of years in just a 30-year period. And what this means for spring rainfall in Iowa is that we are now at our highest level of 30-year average rainfall in the state. On average now, our most recent 30-year average is 13.1 inches of rain in the spring. Our average is about right here on this plot. But what's more important is that what was previously a 1 in 10 year event in the previous 108 years is now a 1 in 3 year event in the most recent 30 years. The same thing can be pointed out for August and July and September, which is what I will call summer for the purposes of this presentation. It's not quite as distinct and quite as strong a shift as a 1 in 10 to a 1 in 3. But what we have seen in Iowa is that our summer rainfall has increased to its highest level in the 30-year average to 8.6 inches, somewhere about here on this plot. And the number of years that are wet in the summer has increased from 1 in 10 during this 108-year period to 1 in 6 during this 30-year period. So there's another way to look at this, and the question is, how similar are the summer and the spring rainfall events? Does one follow another very often? And this plot shows on the x-axis, again, the spring events, that's April through June precipitation, and the summer events, the July through September precipitation for the entire record, 1873 through 2011. Now, the part of the record that's just 1873 to 1980 is in black, and the part of the record that's from 1981 up through 2011, that is in red. And so the way to look at this in a qualitative sense is that when you're in the upper left-hand corner, that means there was a dry spring and a wet summer. When you're in the upper right-hand corner, that means you had a wet spring and a wet summer. Lower right-hand corner, wet spring, dry summer. Lower left-hand corner is dry spring and dry summer. So what you can see is that there's no real pattern to these plots, to these points. It looks like a buckshot. And what that means is there's no correlation between summer and spring rainfall. It's essentially two different rain seasons. What you also can see, however, is that over time, no new correlation has happened. So we know on average there's no relationship between spring and summer. What we can find here, though, is that there might be a relationship between their extremes. And if we had the same plot, but instead of just looking for correlation, we looked at the region of infrequent events, and we delineate infrequency by this circle, then we can see that what has happened since 1981 is that the number of dots outside of the circle is a lot more frequent than the number of dots within the circle. Specifically, what is going on here is the circle encapsulates 95% of the dots, the black dots. That's 1873 to 1980. Instead, if you just overlay the red dots, which is 1981 to 2011, 30% of those dots lie outside of the region. So compared to 5% for 1873 to 1980, we now have a frequency of 30% outside of these circles. And you can also see that it's not just in one way that these dots have become more frequent. Some of them are wetter springs and wetter summers. Some of them are fairly wet springs or average springs and dry summers. And some of them are very wet springs and dry summers, and some of them are wet summers and dry springs. And what this plot is telling us is that the biggest change that we've seen over the last 30 years is that the range of extremes, the distance between our extremes has gotten bigger. Before, when we talked about an extreme event, it was very near this circle. Now, as we talk about an extreme event, it has expanded outward. For those of you who like to think about where you were when an extreme occurred, these are the actual years. These are the flood years in Iowa, 2010 and 2008. There's also 1993 flood up here. Here's the drought in 1988. Here's the drought in 2012. It was about average spring, but then a very, very dry summer for Iowa. Well, there's another way to look at these plots. You can look at it meteorologically. You can also look at it with what people experience. And so, again, we have the same data plotted back behind here with our circle showing the 95% coverage for the previous 100 years. And what I put on top of this are reports that I've gathered, labels that describe reports that I've gathered while talking to people over the last few years. And when you get, of course, to very wet springs and very wet summers, you can get large river basin floods, such as 2010 in the Missouri River Basin. And in Iowa, of course, there was 2010 and 2008. But associated with even just a heavy rainfall in the spring is soil erosion and soil loss. And that's problematic for continuing to have the base to be able to support agroforestry and agriculture. When you have a wet spring or a wet summer, you have to worry more about pathogens. When you have very dry springs and very dry summers, then you can have a statewide crop failure. You could have tree seedling death from a lack of water. You can have poor water quality as well as quantity. Pests begin to become more and more impacting when there is stress from dry conditions during the summer. When it's very dry in the spring and summer, wildfire becomes more of a hazard. And also fish kill becomes much more of a hazard as stream flow becomes lower and lower under dry conditions. So this is one way that we can sort of translate what these new extremes shown by the red dots outside of the 95% region might turn into in our world around us. So that pretty much concludes my first part of the presentation. What types of warm season rainfall extremes have occurred recently? Well, recently we have extreme rainfall days have a higher amount compared with the previous century. And I didn't focus on days, but I'm happy to answer questions about that to clarify later. What I did focus on was the second point, which is that wet spring or wet summer occurs more often compared with the previous century. Again, previously, those events occurred about 5% of the time. Currently, it's occurred more like 30% of the time. And extreme summer drought occurs about as often as the previous century. So what was a 1 in 20 drought continues to be about a 1 in 20 year drought, and we just experienced one last year. So moving on to the next question is, what do projections for 2013, 2020, and 2040, and then out beyond 2040, say about extremes of the future? And this is where we get to be able to translate some of all that work that we do, number crunching to understand significance and probabilities, and putting it into meaningful things, meaningful decisions that people make. Well, I'll begin with 2013, and what I show on this plot are two approaches for looking at a forecast for the spring rainfall in 2013. The rainfall is March to May, and the forecast on the left-hand side is created by looking at historical analogs to the current condition. The forecast on the right-hand side is from a dynamical global model that's run at the National Oceanic and Atmospheric Administration, and that informs the seasonal forecasts that the National Weather Service provides. And so there are two perspectives I want to take on this plot. On the one hand, I'm really happy to see, as a scientist, that there is a green region in the central part of the United States in both plots. The green region means that there is more rainfall expected under these conditions. So under the conditions of what I'm going to call El Niño, and I hope that might be described a little bit more later, neutral El Niño conditions that we're experiencing right now, historically, there's been an increase in rainfall across the Midwest in March and May. This is in units of standard deviation, and it's about a half a standard deviation increase. So it's maybe not statistically significant right off the bat, but it's definitely a sign of hope considering what we've been through. What is also inspiring about this is that a dynamical model, which is only given the ocean state at the current time, so it's given the state today of El Niño, comes up with a similar answer, at least in the space, at least in its location. These are actually in units of deviation rainfall. So this is an additional 0.2 millimeters or 0.4 millimeters per day from rainfall. So as a scientist, this is very encouraging. There are two very different forecast systems, and they show a similar result. And that's basically like an OMG moment for us. We're like, wow, that's great. As a resource manager, though, perhaps I would look at this plot and I would say, there's some agreement here, but what about California? That looks pretty different. There's, yellow here, green there, and what about the Southeast? There's a lot more yellow along the Southeast here. So maybe it works, but it doesn't seem to work very often, is how a manager might look at this. And I think that they're wrong. I don't think they should look at it that way. The reality is, what we're going to see is somewhere in between that thought pattern. And I'm not going to go into explaining why there is a disparity between looking at these plots, but it has to do with the variability associated with rainfall. It's very, very large. So I'm running out of battery. Okay, while they're going to get a battery, hopefully we don't run out. We have a backup coming up. And let me just get to the punchline of this plot before we go on to the next slide. The punchline is, folks ask me all the time, are we in good shape for next year? Are we going to recover from this drought? And what I can tell you from this slide is that our best guidance suggests we're in good shape for this year. The spring looks like it's going to recharge the soil. It has a very good chance of recharging our soil and giving us some water back into our rivers by the time May rolls around this year. Okay, I think we got that settled. So, as I said, there's a lot of complicated science behind this. Perhaps Tony Lupo, who's speaking next, will speak some of it. What I really am interested in is what it means for people who do agriculture, people who do agroforestry, people who do things. And so on the next slide, I'll give one example of how to relate this upcoming forecast to an actual thing that people do. And in this case, it's corn yield. And what I've done is looked at the United States corn yield from what's called the NASS database saved by the USDA. And using 1950 to 2011, I computed a trend. And what corn growers want to know is, are they going to beat trend? Trend is basically their expectation for the upcoming year. And if they beat trend, then they have a bumper crop, and then they can get a surplus of revenue. Well, what this plot shows is when we have an El Niño, when we have a La Niña, or when we have a neutral, which is the case we're in right now, what is the likelihood we'll be below trend? So if we look for both corn and soybean, we find out that under neutral conditions, historically, 40% of the time we have been below trend. That means 60% of the time we have beat trend. In other words, the historical precedence under these conditions is that we will have a good crop year coming up. And what's nice about this is that it's consistent with the previous slide, which says Meteorologically, we expect to be in good shape with rainfall. If we're in good shape with rainfall, you might think we'll also be good shape with crops. Our data analysis of crop yield also then confirms that we will in fact have a good chance of being in good shape with crops this year. So 2020 to 2040 is really a more difficult thing. It's kind of a no man's land for climatology. On the one hand, we know that there is some increased greenhouse gases that will affect our circulation to some extent. We also know that the ocean itself will drive a lot of what happens over the next 20 years. And we have 0 prediction systems available for the next 20 years. Those are things that are just now being developed. Historical data series are too short to provide a precise dynamical empirical model forecast for 2020 to 2040. Our dynamical process models are underdeveloped for the purpose of a forecast for 2020 to 2040. So we have to do some learning and thinking about how to process information in order to make a better forecast for 2020 to 2040. The best we can do right now is take a synthesis of analysis of historical data as well as some experiments performed with dynamical process models to provide us some guidance on 2020 to 2040. So this is a synthesis exercise more than a forecasting exercise. And what our historical analysis shows us is that there's a correlation between drought risk. There's a change in drought risk that's related to sea surface temperatures. This plot shows 4 types of sea surface temperature patterns, type A, type B, type C, and type D. It doesn't really matter for the purposes here today what they are. What matters today is that what's colored in blue and yellow is the likelihood of drought under those 4 patterns. What you see in blue are probabilities that are less than 25%, and what you see in red are probabilities above 25%. And since the mid-1990s, we have been in this pattern where the probability of drought is above 25% for the central part of the United States, stemming from eastern Oklahoma up into Ohio Valley, and then along the southwest and into the Intermountain region. Well, where we are going for 2020 and 2040, if our time series of ocean data conforms to what it has historically done, looks like this. So we've gone from the bottom right, and we are headed towards the upper right. And what that means is there's a higher likelihood, should we continue on this path, of drought conditions across the Midwest, the Great Plains into Iowa, and unfortunately, Missouri does not get a break between the two so much. Well, we can also look at our dynamical process models, and this plot shows the growing degree days, not so much rainfall, but growing degree days are related to rainfall when they are extremely high temperature growing degree days. Then this plot shows for the current century, 1979 to 2000, what the growing degree days are for temperatures above 29 degrees Celsius. So when it's 29 degrees Celsius and hotter, you compute the growing degree days. And this is actually, instead of a measure of growing, it's actually a measure of stress on plants, such as corn, perhaps trees. And on the lower left-hand corner is the variability from year to year in that. So you can see that Missouri is in a gradient from a high stress area to a low stress area. Iowa is also on this gradient in Illinois. And the variability is very high here in Kansas and into Missouri. These simulations that have been performed for 2020 to 2040 shift the area of stress northward into Kansas and also Missouri. It shifts the area of variability quite a bit farther northward into Minnesota. And on the right-hand side, they have shown a way where they have said that in the current century, the blue region is where the temperatures are highest. And in this 2020 to 2040 period, the red region matches the temperatures of the blue region. And so you can see the northward migration of this zone of stress. And then not only that, but the northward migration of the zone of variability in stress. So this is consistent with what we were just showing in the previous slide. It would suggest that there's more drought risk, and more important, when there is a drought, higher temperature risk in the 2020 to 2040 time period. Well, coming back, I'm going to sum up on that in a moment, but I want to go farther ahead now to 2040 to 2100. In this time period, we have to use climate models pretty much exclusively. And the reason is that the recent rate of increase of greenhouse gases is not something that's found in the historical data. And so it's hard to find analogs and proxies to figure out what the future might look like. The climate model projections, unfortunately, do not capture some of the variability, some of the things that cause the climate to change. For example, they don't capture all the solar variability. They don't capture volcanoes or changes in aerosols and other factors that cause the climate to change. So, climate models for 2050 to 2100 do not provide a forecast in the same sense as a seasonal forecast for 2013. What I showed you earlier about 2013, we could actually calibrate the probabilities and make it a well-calibrated probability forecast. That's not the case for long-term projections. Instead, what we are saying is that they provide an expected response to one climate change mechanism, greenhouse gas increase. Well, here's some data that shows what those simulations are providing. These data, again, are for Iowa, and it's for April through September rainfall. And on here, I've plotted in black the historical record. I showed you earlier the spring and the summer part of this historical record. Now here's the spring and summer combined. And in the colored part are scenarios, are these simulations run by global climate models, and then having an empirical algorithm applied to them so that their daily precipitation and daily temperature values have some sort of error correction. And the point of this plot is to show that over this period where the historical data and the climate model corrected data have overlap, you can see that the range of extremes are fairly similar. The climate model projections have fewer more droughts than were observed. The droughts being as low as 30 millimeters of rainfall during April through September, whereas in the real world, the worst droughts were more like 37 or 40 millimeters during April through September. But they have very similar magnitudes for the floods, between 95 and 100 millimeters in April through September. And the point of this is that our recent trend, which you can sort of make out here, of an increase in the width of extreme events, continues forward in time through 2100. The main thing is that if you look at the mean, there may not be much change at all, but the distance around the mean of rainfall extremes is bigger. This is reflected also in the middle part of this century, if you break it down by season. Returning back to spring and summer seasons, here we have the spring season for the central United States, and on the vertical axis is the precipitation change in percent. And these models that have been, again, empirically corrected against observations show an increase by middle part of the century of about 10% of rainfall. That's roughly what we have seen as an increase since 1950 in Iowa. So it's basically continuing the trend that we've already seen for the last 50 years. For summertime, it has an interesting pattern that is hard to explain and hard to know. So when I talk to managers, I really don't know what to suggest about this. It has a future where there are warmer and wetter summers, and some futures where there are very, very dry and very, very hot summers. And it shouldn't be surprising. We all experience that when it's dry, it's much hotter in the summer. That's intuitively correct. But what's weird about this plot is how you divide up the global climate models. If you divide this plot into the global climate models that come from the United States, those that were developed by NOAA, NASA, and other agencies in the United States like the DOE, all of their simulations are up in this cloud, warmer and wetter summers. If you look at the models that were developed outside of the United States, Australia, Europe, Japan, they lie here along this axis that shows potentially drier and hotter summers. So there's something different in the way non-United States models simulate the summertime climate. And I don't know what to put stock in, to be blunt. But what I can tell you at this moment, that's something that researchers have to understand better before we can actually tell resource managers this is actually credible and this could possibly be our future. I don't think we can actually say that right now. What will need to happen is we'll need to have further study of the summertime dynamics to understand whether these models are producing regional dynamics, the dynamics within the region, that are credible. So at the moment, the best that we can say is we'd have to prepare for a much broader range of summertime outcomes. And as we analyze the data, perhaps these will become, these warm, hot summers, these dry, hot summers, will become less credible in our sight as scientists. So finally, putting this back into our plot that we showed earlier, if we take that increase in mean rainfall as well as the variability, the increase in variability primarily in the spring, which lies along the x-axis, then what was our 95% region for 1873 to 1980 turns into this red 95% region for the middle part of the century. And you can see that what happens is with little change in the summertime mean, it doesn't really change, this region doesn't really change much in the vertical axis. You still get very big droughts. What does change the most is in the springtime and in the summertime, you get an expansion into more extreme, what are currently very extreme, wet conditions. And we can go back, oh no, I'm sorry, I think I have the slide later. I gave up my punchline. So what's going to happen is, I almost gave up my punchline. I forgot that I had this slide, and I don't really want to talk about this anymore because I'm running out of time and it's too complicated. But what this slide represents are hot off the press results. Literally, this is the next round of global climate model simulations that have been completed for the next assessment for climate change, international climate change assessment. What I wanted to show you is that this plot in the upper left-hand corner is called the multi-model ensemble. Every single one of these images represent a spatial pattern of temperature change in the climate model simulations. And this one in the upper left is the average of all of these. And if you compare the average to observations, this is the difference pattern, or how different from observations the average of all the models is. You can see it's a little bit cooler in this plot of December, January, February in Central America, a little bit warmer in the Northeast. And I just wanted to orient you to see how people are using the newest global climate simulations to give you a perspective on what the next slide means. So the next slide shows for 2070 to 2099, the rainfall change of the multi-model ensemble mean. So again, this is an average over all those 13 models that were shown, and the average that I talked to earlier in the upper left-hand corner. And what it shows is that in the summertime, there's almost no change in the mean precipitation. And if there is a change, it tends to be a little bit drier in the plains area of the central United States. So in summary, what projections for 2013, what are the projections for 2013, the near term 2020 to 2040, and the long term 2040 to 2100? Well, it appears that in 2013, a dry spring or summer is unlikely, given historical precedents and given our forecasts and the agreement between the two. 2020 to 2040, a synthesis of our scientific and peer-reviewed literature suggests that there is a chance for a higher frequency of drought and an increase of temperature when there are droughts occurring. From 2040 to 2100, then it appears that the warming climate will have an increasingly greater impact on rainfall variability. That means we'll have a broader range of extreme rainfall. So finally, what are some considerations for agriculture and agroforestry? And you should surmise already that adaptation is going to be something that we're going to have to do. And this is one of my favorite things that I've seen developed, this idea of water from air, where in Australia, an engineering student has taken a design based upon a beetle. And in these coils in the ground, they have air that flows through them. And the design from the beetle allows the air to condense onto the coils. and that provides water that can go into irrigating at the roots of these systems. And so they drive this whole system by having a propeller here, wind energy, that pushes air from the atmosphere downward into the coils. The coils convert the air from humid air into water. And then that whole system is driven either by solar energy or, if there's enough wind, by wind energy. And so these kind of adaptations are the real inspirations and the real innovations I think that we need to start thinking about in order to deal with a wider extreme of precipitations in the future. Here's a slide that I thought I had earlier that I call my punchline. So coming back to this nice red area of 95% for the rainfall in the summer and spring, then we can overlay that with the impacts that we've already experienced under the current system. And as it shifts towards wetter spring and a slightly wetter summer because of the variability change, then that means this would suggest that we're going to see more of the medium river basins have floods, that maybe because of wetness we might have more statewide crop failure, that we need to address soil erosion and soil loss through soil conservation measures, that we need to start thinking about our pathogens and the way we control them. Again, for those parts of the state where they put a lot of nitrogen on to grow crops, this is something else that we'll have to have a stronger control on in order to keep our drinking water supply clean. Here's one nice thing though. If you're into growing grapes, it looks like a really good environment for growing grapes. It becomes more and more like a Mediterranean environment, in fact. So moving on, finally summing up, how do we think about going forward, adapting to these wider ranges of extreme conditions? And the U.S. Forest Service has put together at least a typology that gives us a language that we can talk to each other about when we start prioritizing and classifying our adaptation strategies. They describe a resistance strategy, a resilience strategy, and a transformation strategy. A resistance strategy builds resistance to a changing climate, whether by greenhouse gases or otherwise, in order to maintain the status quo over the near term. So let's say in the near term we're expecting more droughts in 2020 to 2040, but we want to maintain our water supply at the current levels. Then building resistance would mean developing strategies to maintain our current levels of stream flow in the face of increasing frequency of drought. Resilience strategies means building adaptive capacity by improving the system's ability to moderate effects of climate. So perhaps it's not enough to figure out a way to keep water around when it isn't raining, gather water when it rains and keep it around when it's dry. Perhaps we need to do something to the way that water flows into the rivers to keep the water handier. And then finally, a transformation strategy means you increase the adaptive capacity. And this usually requires the system to have some sort of new components, some sort of redesign of the whole system itself. And so my final slide in this section is more directed towards how to use climate information in understanding these different adaptation approaches. I think there are going to be a lot of nice presentations here very soon that shows many different ways that we may need to adapt and the really smart engineering approaches that can be done. In my role, I can help you understand what climate data are useful for looking at different adaptation strategies given the new system development ideas that people present. So for resistance strategies, the most obvious thing and the most immediate thing is to take advantage of seasonal forecast information. And I showed earlier that the possibility of thinking about March through May rainfall just in 2013. The question you might raise is, if we really believe that 2013 has a better chance of giving us more rain than 2012, what should we be doing to take advantage of having that rain? What can we do now to take advantage of having that extra rain? That's an idea that fits into a resistance strategy. Basically, we augment our monitoring, for example, with drought forecasts. And the reason why I point out drought forecasts is that the National Oceanic and Atmospheric Administration has put a lot of money and time into improving their drought forecasts recently. They were urged on by the Western Governors Association in the early 2000s, and so they have about 10 years of infrastructure development. And out of this, there are some recent reports that show their dynamical models have improved considerably in being able to predict droughts. And so now is the time that we could possibly take advantage of this and merge it with other techniques that are equally valid and equally effective at forecasting droughts. The most important thing, though, is to think about it in terms of a management perspective. If you knew the information today, what would you be able to do? That's the question that a resistance strategy would address. A resilience strategy would tend to address the questions of vulnerability. What are the limits of our system? And in order to do that, you would primarily use historical climate data. You would take an existing system in place, and using the historical climate data, you would actually have to either design some sort of tweak to the system, or perhaps maybe design some sort of tweak to the historical data to figure out at the edges of the climate data, at the extremes of the climate data, what is the vulnerability of the system to failure. So historical climate data are very useful for this. And by historical data, I don't mean just the data record dating back to 1873. You could also use paleoclimate data, which might have times in the past where there are greater ranges and extremes than we've experienced today. And then finally, transformation strategies where we build new systems. Well, the only way we're going to have any certainty whatsoever that our new systems can actually transform the way we manage water and be able to survive what the future climate might look like is to link it with process models into the climate projection data. And so this is a complicated process that usually requires quite a bit of effort on both sides, the side of the climate scientist and the side of the process modeler, in order to communicate how that climate data must be delivered and is most appropriately given to the process model. So this is a much more complicated and in-depth study. Now, some of you may have heard of what are called the Department of Interior Climate Science Centers. And these climate science centers are generally tasked with supporting this kind of effort. And I can't speak for the Northeast, but in the North Central, one thing that we are building is the climate data sets along this three-tiered structure so that people can come in and get not only the climate data that is relevant for ecosystems, forests, wildlife, but also they can get guidance on perhaps what kind of climate projection they might want to use. It'll have built into it some expert opinion, some expert judgment, and that way you won't have to hire a climate scientist every time you want to do one of these studies. All right, so here's my ending slide. Here's exactly what I want you to take away from this whole presentation. The Midwest Farmscape will experience a widening range of warm season rainfall extremes. The recent history has seen an increase in frequency of years with either a wet spring or wet summer or both. By 2020 to 2040, a synthesis of peer-reviewed climate literature indicates a higher frequency of drought may return. Beyond 2040, both drought and rainfall are expected to reach new extremes, even if average rainfall is relatively unchanged. This indicates the need to adapt. Adaptation that prioritizes resistance, resilience, and transformation strategies should evaluate, respectively, seasonal forecast data, historical data, and future projection data. And our recent findings show promise for integrating seasonal drought forecasts into drought planning. So I think we're just getting started on thinking about how to adapt, and there's a long way to go before we can even say that on the ground we are adapting. But we have a really good foothold that we can make with seasonal forecasts. And we have a really good idea that what we need to worry about in our systems is a wider range of extremes. And I think that gives us at least boundaries that we can march forward and begin thinking about how we need to organize our society, how we need to manage our risks, and what we can do over the next 10 years so that what we experience in the future is less costly than the last 10 years. Great, thanks.
Thank you, Chris. We've got some time for questions. We have microphones set up here in a couple places if any of you have a question for Dr. Anderson.
It's not a problem if you don't. I'll be around all day, so if something comes to mind later, just stop me in the hallway and ask me.
Were those predictions based on several models or just comparing one model?
On
how they were related, each model?
So in the 2013 forecasts, that prediction was based upon a single model. That is the model that is run by the National Oceanic and Atmospheric Administration. What they have just invested in over the last 2 years is the capability to run multiple models. And so there is not quite yet long enough history to do a very rigorous comparison with what other models would say in the United States for 2013. But what the one plot showed is that compared to just a historical analysis, the results are in line with expectations. And so that's where I think for 2013 we borrow some confidence, is that our model isn't predicting something that's unusual. It's predicting what we've seen before. For 2020 to 2040, there is not really a clear model. And what I showed is just results from one model. And even though I showed it from one model, you'll have to take my word for it, but it is consistent with what other people are saying. I think in the near future, we're going to do a much more detailed analysis of 2020 to 2040. And hopefully then in the next 5 years, have a little bit more we can say to you with rigorous simulations and a strategy for prediction. And then for 2040 to 2100, the couple of slides I showed there were based, well, in the 2040, in the mid-century, 2040 to 2070, that included all of the 121 simulations that were done for the previous international assessment on climate change. The most recent plot that I showed for 2070 through 2100 is based on 15 that were completed in time for the current international climate change assessment. So that is very preliminary. They just finished the runs in the middle of 2012, and they have just released the results in December of the very first analysis. What they are seeing, though, is that there's a lot of similarity between what the previous international climate change assessment reported and what the current simulations are producing. So I don't expect there to be any large surprises, especially for the central United States. The main message of extremes being wider, but the mean change being not so interesting, not so much, is probably what's going to come out of this assessment, and it's right on target with what came out of the previous assessment.
Shmuel.
Chris, I wanted to ask you about the US model versus non-US models that you showed, that the US models predicting one thing and the non-US models predicting the totally opposite thing.
Yeah.
Are they based on historic data, or why
No.
do you see something like that
These
in predictions?
These are dynamical process models. So the way that this data gets generated is that a climate model must be brought to some state of dynamic equilibrium or some sort of dynamic balance. And what happens is a climate model is then run for maybe 1,000 years so that the ice and the sea, the ocean and the land and the atmosphere reach some sort of dynamic balance. And then it is given conditions, greenhouse gas conditions that conform to today. And for a period, about 100 years, 150 years in fact, actually, it's run with solar variability as best as we can estimate it from measurements, volcano variability, greenhouse gas variability. And for those 150 years, it's meant to replicate what we just have experienced from 1850 to 2000. Then from 2000 on, the only factor that they give to the models is the greenhouse gas change, because it's very difficult to predict the future of the solar radiation variability, the future of volcano variability. So the process model takes the changes in radiation, which is the source of all the energy in our climate system, and it makes changes in that radiation only based upon the greenhouse gases, not based upon the sun, not based upon the volcanoes, in the period 2000 to 2100. So that's what these represent. This is 121 simulations of that future period from the process models. What was your question?
Well, the question is, when you use even a dynamic simulation model, you would think that they would all predict the same thing, or at
Right.
least similar. But here, you are going in two different directions. And why?
So I suspect there are two ways that this could be different. One is in the central United States, what determines our rainfall in the spring is the position of the jet stream. A secondary component that meteorologists don't often study, but that hydrologists study, is the amount of water vapor that's coming up off of the ocean. So those two components, the jet stream, when it comes across the United States, squeeze water out of the air by the storms that it puts through the United States. And the amount of water that's in the air is due to the amount of water that comes off of the ocean. And so in the springtime, what you see is there's not a lot of disagreement. And that suggests that those processes are very, very similar in those models. I mean, there's a lot of variability here, but there's nothing like what you would say is a bifurcation as we have in the summertime. One models go one direction, another model goes the other direction. Well, my hypothesis, and it would be really nice to get funded to study it, is, and those of you who write grants know what I mean, is there's a soil moisture feedback in the Midwestern United States that global models, I don't think they handle it very well. And I think that's what we're seeing here. In Australia, in Central Europe, there's an expectation that the interior part of the continent will become drier. If you have a warmer summer and you no longer in the summertime have an influx of moisture into that region, your soil just dries out. That's the only source of water that you can find. And when the soil dries out, it gets hot. But what happens in the United States is, of course, we have a source of water from the ocean during the summertime. And we have nighttime convective systems, and those things are not at all simulated well by global climate models. Now, it appears that the US models have some sort of representation of that, whereas the European models, where they don't have that process, does not have a representation of that. That's my hypothesis. And thanks, Tony. And if there's not I forgot that I was going to tell my story. If you wanted me to tell the story about the beaver dam and there aren't any other questions and you have a couple minutes, okay, I will then. So that story relates to this plot. 2012, in the summertime, is down here for Iowa. That's the rainfall, just barely over 5 inches of rainfall we got during July through September in Iowa. And you can see there were a couple other times when we were close to that, 1977. And by the way, this means we beat 1988 in the summer by a fair amount. It's not even close. 19 looks like 47, and back here in the 1800s. Well, what happens in Ames, Iowa, is that our drinking water comes from an aquifer that sits underneath the city. And the water that gets into the aquifer drains through the stream bed of the Squaw Creek. It really is a creek. It's not very wide. Now, what happens when there isn't any water in Squaw Creek? There's no water going to our aquifer. If there's no water going to our aquifer, then we don't have any water to drink or to do what we do with water. So while this looks like a beaver dam, it was actually built by the city of Ames. The city of Ames went out there and collected sticks and twigs and built a makeshift dam this last year so we could maintain our aquifer through the winter because we just didn't have any water in our stream just on the northeast edge of town. I like that story. It shows the urgency of 2011 or 2012. It was hard to predict and plan for it.
Chris, thank you very much. I think you did a wonderful job both telling your own story but setting us up for the talks to come and the discussion over the rest of the day. If you would all join me in thanking him again for a wonderful presentation.